nanofibers is an area that has blossomed in about the last 10 to 15 years. The technology for making nanofibers actually is relatively old, going back maybe 100 years to some early patents at the beginning of the last century. But the blossoming of the technology really expanded in the late 90s, early 2000s with the invention, with the rediscovery of a technology called electrospinning. Now, fibers historically have been around for a very long time. There are natural fibers like cellulose and silk that have been used by people for a long, long time. And there are these engineered plastic fibers that were developed in the last century, like nylon and polyester. But what's really unique now is our ability to make these fibers with diameters, continuous fibers with diameters below 1 micron in diameter. Using these technologies, we can make fibers that are perhaps on the order of as small as 10 nanometers in diameter to 10 microns in diameter. So to give you an idea of what this means, the human hair is around 50 to 100 microns. So we're talking about 10 to 100 times smaller than the average human hair. Okay. Now, beginning around the mid to late 90s, a process called electrospinning or electrostatic fiber spinning, fiber formation, became popular because it uses electrical forces rather than hydraulic forces to draw out the fiber. One can make nanofibers using conventional fiber spinning techniques, which are hydraulically driven techniques, but it's very costly to do so, and one can't always get it to work for any kind of plastic. Whereas this electrical processing technique turns out to be very robust, very simple to implement, and very rapidly makes a large amount of very fine diameter fibers. So if you look back historically to about the year 2000, 2001, there probably were 10 publications and 1 or 2 patents in the area of this process called electrospinning, or the formation of nanofibers. They simply didn't exist broadly. In the intervening 10 years, this has grown by 2 orders of magnitude. The publication record has grown to 1,000 to 2,000 papers a year. There are now something on the order of several hundred patents per year in this area. And both the science of nanofibers and also the industrial commercialization of nanofibers is going through a very rapid expansion phase as people, scientists and engineers, try to figure out what unique properties do these really bring and what's the low-hanging fruit, the opportunities to take advantage of this unusual and heretofore not really available material, this nanofibrous material. So we have viewed this development of nanofibers as an opportunity to look at the connections between the structure and the properties of the plastic. By virtue of making these very small diameter fibers, we alter the structure and organization of the molecules within the fiber. And so we expect different properties of these fibers than their larger, more macroscopic counterparts. And so we study the fundamental organization of the molecules within the fibers, and we correlate those or develop models to explain how those give rise to perhaps stronger mechanical properties of these fibers, which are sometimes observed. Also, the way these fibers organize themselves into larger materials. So it's typical to make a sheet of these nanofibers, much like you would have a tissue paper or a sheet of paper. We can make sheets of these nanofibrous materials out of a variety of different polymers. And these sheets have very interesting properties. Of course, the fibers that make them up are very small in diameter. So let's say 1 to 200 nanometers in diameter for the fibers. This imparts to the sheet a very high surface area. So the specific surface area, the area per unit mass of the sheet, may be on the order of 10 to 100 to even 1,000 square meters per gram. And so you can begin thinking about decorating this surface with functional groups that impart some kind of functionality to the plastic sheet. At the same time, fibrous materials, non-woven fiber sheets, by their nature, tend to be relatively porous, open weaves. Well, they're not weaves, they're non-woven. So they're very open structures compared to an equivalent type of material that you might make with a film or a collection of nanoparticles, which pack much more densely. So we can get very high porosities, but at the same time, because of the small size of the fibers, we can maintain very small distances between the fibers. So think of this as a very small pore size material. So when you have high porosity and small pore size, this is a natural membrane material. So one of the early applications for these nanofiber materials was in the filtration industry. So people, companies who develop high efficiency particulate accumulators, HEPA filters, very early on discovered the possible applications of nanofiber materials as a component of their commercial air filter materials. But there's a lot more that we think can be done with these nanofiber materials, and that's where our lab comes in to show what's possible with nanofibers by making it out of different materials, by decorating them in different ways, by showing how their properties arise from the way the fibers are made and what they're made of. And so, for example, we think there are applications in not just air filtration, but also producing clean water applications. So right now, in a lot of areas of the world, desalination is a big concern. Reverse osmosis, thermal desalination and reverse osmosis are the two dominant technologies for that purpose. But there are a lot of other technologies that can be used that can take advantage of the particular pore structure of a fibrous material. There are also technologies for removing salinity ions, salt ions from saline water that take advantage of what's called some kind of electrical properties, capacitive deionization, for example, that take advantage of the high surface area that's possible in these kinds of membranes. So now we can start looking at devising new types of membranes for water purification, desalination. We also look at them for other types of water purification. So oil-water mixtures are a common source of contaminated water. Think about the Deepwater Horizon oil spill in the Gulf a few years ago, or the large amounts of contaminated water that are brought up to the surface as a result of hydraulic fracking to produce natural gas. These are all contaminated water streams that we think we can remove a lot of the contaminants through using these nanofibrous membranes as filter materials, because they can be designed so that one component, either the oil component or the aqueous component, can pass through the membrane selectively.